Remember that we're interested in finding the shape of a hanging cable, and I told you that we're going to derive a differential equation to do this. And that's really what we want to show you in this video, is how does one find a differential equation, because this is often the interesting part of developing a model, is actually coming up with the differential equation. So in the last problem, I asked you to think about what tan theta means in terms of our picture. And hopefully you were able to deduce that tan theta is the slope of the tangent line to this curve at the point xy. In other words, tan theta is equal to f prime of x, which I'm going to write as y prime for simplicity. So now we have something that is starting to look a bit like a differential equation. We have that s over a is equal to y prime. Of course, at this point, it seems we're stuck. We don't have a formula for the arc length in terms of x and y. Don't worry, we'll get there, but not for a while. So what can we do? We know that this equation is true, which means it's true if we pass to the differential as well. That is, d of s over a is equal to d of y prime. Since a is constant, this is saying that 1 over a ds is equal to dy prime, which is of course equal to y double prime dx. So what is ds? Remember that ds is an infinitesimal piece of this curve. And when we zoom in on this curve, it looks like a straight line. And so this is my line segment ds. We can think of this as the hypotenuse of a right triangle with sides dx and dy. So ds is equal to the square root of dx squared plus dy squared. I'm going to write this in a more suggestive way by pulling out a dx from the square root to get that ds is equal to the square root of 1 plus y prime squared dx. So now we have a differential equation involving only x and y, which is what we're looking for. And 1 over a, the square root of 1 plus y prime squared dx equal to y double prime dx, holds on all infinitesimal segments along this curve. So in fact, this equation is true even without the dx on both sides. So let's go ahead and erase that. And what we're left with is a differential equation. 1 over a times the square root of 1 plus y prime squared is equal to y double prime. And because our curve satisfies this differential equation, the shape of a hanging cable is a solution to this differential equation. So that's what we want to find. Before watching this video, you saw that the function that satisfies this differential equation is y is equal to a times cosh of x over a, the hyperbolic cosine. Here, a is the amplitude of this hyperbolic cosh, which determines the steepness of the curve. So that's why I used the variable a for the constants involving horizontal tension, gravity, and linear density, because what it is giving us in terms of this curve is behaving like an amplitude. Note that this is in fact a separable differential equation, but our only tool for integration right now is u substitution, which was going to be pretty tricky to see in this particular case. But we really like examples that relate it to the zip line because this is actually a really tricky problem. So instead of focusing on solving the differential equation, here we wanted to expose you to how differential equations arise in real-world modeling problems. And in fact, oftentimes you might be more interested in deriving the equation than finding a solution because there isn't always a nice analytic solution. We often resort to finding numeric solutions instead. We'll come back to this example later once we have some more techniques of integration. But for now, the next video in Mathlet explore the problem of modeling the zipline to see how the two limiting cases are related to a real zipline trajectory. And I hope you'll start to get a sense of just how complicated this seemingly simple real-world problem really is.